Okay. All right. So yeah, I was saying telling some friends the last time I was in Philly was about 15 years ago, and at that time my talk actually went about 40 minutes over, and everyone in the audience was too polite to stop me. So if I start going over, please stop me. Right. So let me say a little bit about. So I'll spend most of the lecture talking about algebraic K-theory, and depending on time at the end, I'll say maybe a little bit about the topological K-theory. So the setup here is the following. So we start with a ring R. So a ring with unit. And we would like to try and analyze representations over R. So, or matrices over R. So given a ring, we can consider, so we form GLNR is going to be, so n by n invertible matrices. And here by invertible, I mean two-sided invertible with coefficients in R. Okay, so these are the sorts of things we might be interested in studying. And so from the classical theory, we know that a useful tool for studying matrices is the determinant. So the first question is, well, what is the appropriate analog? So determinant in this setting of general rings for GL and R. Okay. So already, if you think of a 2 by 2 matrix, so the problem is the following. So if you've got a 2 by 2 matrix, A, B, C, D, and you try to define the determinant the way you usually do, right? So you might want to define it as AD minus BC. And this is all fine and good if your ring is commutative. But if your ring is non-commutative, then you've got a problem, right? Do you take this as the determinant, or do you take this or this, right? dA minus CB, etc. Right? So there's lots of choices there. And it's not clear. None of these are canonical. There's no reason to prefer any one of these over any other. Okay? So these can all be different. If R is non-commutative. Okay. So the way around this is to instead look at the properties that we like about the determinant map and use that to formulate the right definition in the non-commutative setting. Okay. So what are properties? So instead, find properties we want determinant to have, and use this to motivate the correct definition. Okay, so what are some nice properties that determinants have? Well, so two key properties we're going to want to preserve. So key properties. So the first property is that determinant is invariant does not change under elementary row and column operations. Right, so this is all basic fact. If you add a multiple of a row to another, your determinant doesn't change. And the other property it has is if you augment, so does not change when you augment with a trivial map. So i.e., so what I mean by this is if you look at the map, so determinant of A is the same as the determinant of the block matrix where you augment with a 1, right? Those two determinants are exactly the same. Okay, so if we want to define a determinant in a non-commutative setting, we're just going to use these to define what it should be, right? So we say, so definition. So we say that two matrices in GLNR, so matrices in GL, okay, so now I'm gonna pass from finite matrices since I want to allow augmenting. So matrices in GLR, so this is going to be the union of GLNR under these inclusions, where you can think of n, as an n by n matrix as a larger one just by tacking on ones, are equivalent. So we're now defining an equivalence relation on this. And how are they going to be equivalent? Well, if they differ by elementary row operations or by augmentation. Okay? If related by 1 and 2. Okay? Well, so this is just saying that you can think of some GLN as sitting in any of the larger ones. So really, it's the first relation that we now want to focus on inside GLR. And what's this first relation say? Well, two things will be related. So notice that this means that two matrices are related. So after you augment them so they have the same size, A is related to B if you can multiply, so if they lie in the same left coset of the subgroup generated by elementary matrices. And the same coset of the subgroup. So let's say E of R. So this is the subgroup generated by elementary matrices. And so elementary matrices are matrices that have one on the diagonal and a single non-zero entry off of the diagonal. So here's a fun fact. Left coset or right coset? So in this way, I'm writing it as so ER is going to be multiplied on the left. So whichever. Yeah. So here's a fact / exercise. So ER is in fact a normal subgroup. It's in fact the commutator subgroup. Okay. So this actually is not necessarily true at any finite stage. You do need to use the augmentation in order to check this. Okay. And so in particular, so now we can give a proper definition. So this is K1 of R, the first algebraic K group of R is defined to be the abelianization of GLR. So it's GLR mod elementary matrices, equivalently GLR. I guess now I'm thinking of it. Yeah, maybe I want it on the other side. So, question?
So you're talking about the subgroup generated by elementary matrices in that disjoint union?
So it's not a disjoint union. It's a union under these collection of inclusions.
So
yeah. So you can think of, so something in here is an equivalence class where you view a matrix as equivalent to any of the larger ones you get by augmenting by 1. So, okay, so this is K1 of R. And then what's your determinant map? Well, your determinant map is you take a n by n matrix, you think of it as sitting inside GLR, and then you just look at its image in this quotient. Okay. All right. So at this point, I haven't said much about this. Let me. So in a few minutes, I'll give some motivation of some things that are interesting about these. But let me define now for you. So this is K1. Let me define lower K-theory.
So when R is commutative, this is aggregative.
With the usual, yes. So lower K-theory. So now I want to define, so Ki of R when I is less than or equal to 1. And for this, so there's different ways. I'm giving you sort of the quickest way to define it, though the motivation might be a little hard to see at this point. So you define a suspension functor sigma from rings. What's that? So let me. Is that better? Okay. So you define a suspension functor from rings to rings. And the way this is defined is the following. So given R, you form, so consider, so matrices R. So here I'm going to look at matrices that have only finitely many non-zero, so only finitely many non-zero entries in each row and column. And the point here is that this is now, again, a ring. You've got only finitely many entries in each row and column. You add two such matrices, you still have only finitely many non-zero entry in each row and column. And you can also multiply them, right? If you had infinitely and some infinitely many entries, then you could run into convergence problems. Right? You'd get some infinite sum. That doesn't really make sense in a ring. Okay. But this now here is a ring. And within this, you can look at the subring, which are the finite matrices, and these are 0 outside a finite block. Okay? So this here is actually an ideal. So this is an ideal in that collection of matrices, and then you define sigma of R is this quotient here. Okay. And then the lower K-theory is defined by applying the K1 functor to the suspension. Okay, so K1 minus n of R is defined to be K1 of the n-fold suspension of R. Okay. All right. So maybe let me give you a fact, since at least K0 is something that you might have encountered in other settings. So fact. So if you look at K0 of R, so that's K1 sigma of R. So this coincides with the Grothendieck group associated to the semigroup, so finitely generated projective R modules under direct sum. Okay, so if you take finitely generated projective R modules, you take the direct sum, you're back in here. So that forms a semigroup, and then you can complete that to a group, and that, it turns out, is the same as this K0 far that you get in this manner. Okay, that's all I wanted to say for definitions. So now let me ask a question which I'm sure you're all wondering. Why do we care? So, topologists care. Why do I care? And the reason is that for many natural problems that arise in geometric topology, you have obstructions that appear in these algebraic K-theory groups. So for many topological problems, obstructions live in. So the algebraic K-theory of some integral group ring, typically. And here, usually, G ends up being fundamental group of the space you're studying, or yeah. So I'll give some concrete examples in a second. And equally interesting, for many of problems, in fact, all obstructions are realized. Okay, so let me give you some concrete examples of this. Yes. So, yeah, so that's something which I actually don't know the answer to, but I've often meant to look it up. I think it has to do with, my guess is that if you start with a ring that's like a ring of functions on a space, and then if you apply this process, the ring you get should be related to the ring of functions on the suspension of the space. So that's my guess, but I don't know for sure. Yeah, every time I've given this talk, I've said, oh yeah, I should go and check that at some point, because somebody always asks, and I always forget as soon as the talk's over. So, but yeah, so remind me after the talk, and I'll try and look it up. So, right. So yeah, so let me give you a first example. So the first example is the Escobar-Cobordism theorem. So this is Bardeen, Mazur, and Stallings. So here the question is the following. So an H-cobordism, so remember, so you may or may not have seen this, but an H-cobordism over a manifold M, so let's say this is dimension n, is a manifold with boundary. So here I'll draw you the picture. So here's my M, maybe with some topology. So manifold Wn plus 1 with boundary. So I'm going to decompose the boundary into a top and a bottom. And this bottom part here will be identified with M. So you've got something like this. So here's my del minus W, del plus W. So here we might have some topology inside. And the condition, the H part, has to do with the inclusions, del plus or minus W into W. So the way this sits in here are deformation retracts. Okay, so what that means is you can take all of W and you can push it down to M while keeping it the identity down here. Or if you want, you can push it up. So there's one obvious example of this. Right, so what's the obvious example? Well, you take M across the interval. Yeah. And now you can ask, are there any others? Okay. So here's the, so I should say, yeah. So in the case where M is simply connected and high dimensional, so I think you need dimension at least maybe 5 for M. So the fact that the only such H cobordisms, that's the question, is W M cross I, the only H cobordism. And the answer is, so I should specify here, when I say topological problems, these are in high dimensions, so maybe dimensions at least 5. Low dimensional phenomena tend to behave very differently. But in high dimensions, yeah. So the answer is yes, if pi 1 if M is trivial. And this was Smale. And this was crucial in his proof of the Poincare conjecture. Okay. But the answer is no for some other, M. So of course with non-trivial pi 1. And the S cobordism theorem precisely identifies when this happens. Yes? So yeah, the dimension there has to be at least 5. Yeah, so throughout, everything I say now will just be in high dimensions. Yeah. So, and here, the theorem is the following. So this is the Barden-Mazur-Stallings BMS. Is that if you've got any such H cobordism, so there is a bijection between H cobordisms and elements in, oh shoot, I should have defined the Whitehead group. So here, I'll define it right now. So Whitehead of pi 1 M. And this here is you look at K1 of the integral group ring. So you look at this equivalence classes of matrices whose entries are in the integral group ring, and then you quotient out by the commutator. Now, within K1, there's an obvious subgroup which consists of just the 1-by-1 matrices whose entries are plus or minus a group element. So you want to quotient out by those. So if you throw away sort of the obvious elements inside K1, what's left is this Whitehead group. It's the non-obvious elements in K1. Okay. And G here is, yeah, pi 1 of M. Sorry. Yeah. Thank you. Okay.
Sorry, the
So.
integral group ring is the group generated by elements of pi 1?
It's formal sums. It's finite formal sums of elements in pi 1. And then the multiplication uses the group operation to multiply group elements. Yeah. So. Okay. Any other questions, or are people okay with this statement? So now this is sort of, this sort of motivates why you might be interested in K1. So on the one hand, if you know a vanishing result for K1, or you know, I guess for the Whitehead, so the K1 will always be non-trivial because of this. But if you have a vanishing result for the Whitehead group, then that tells you that anytime you have an H cobordism, it's automatically just M cross I. On the other hand, a non-vanishing result allows you to construct funny H cobordisms. Okay, so spaces where these include, but it's not just a product. All right. Let's see. Should I give? Yeah. Let me give one other example. So the wall finiteness obstruction. So here the question is the following. So these are examples of topological problems whose solutions involve algebraic K-theory. So the question here is the following. So given a CW complex, so let's say X, is it homotopy equivalent to a finite CW complex? Okay, so I just give you something. It's got infinitely many cells flopping around in all sorts of dimensions. And I want to know, can I replace this by something homotopy equivalent that only has finitely many cells? Okay, so there's a necessary condition. So you need to, so necessary condition. You need this to be finitely dominated. So I need X to be finitely dominated. If that doesn't happen, you've got no chance. So this means, so i.e., so you need a map from X into some Y. So this is finite CW. And a retraction, so a map R going the other way. So I'm going to call these I and R, such that if you compose, so R composed with I is homotopic to the identity on X. Okay. So X looks like a retraction of something that's finite. So if it's homotopy equivalent to a finite CW complex, you can certainly do that. And then the question is this necessary condition also sufficient? And so this is where the wall finiteness obstruction shows up. So then theorem wall. So there's a bijection between the CW complex is homotopy equivalent to a finite CW complex. So actually, in that case, I don't think it's a bijection. So there is an obstruction. Yeah, so let me correct. So there is an obstruction. So given this picture here, there is an obstruction sigma of X. And this lives now in, okay, so I should, so a reduced K0 group of, again, Z I1X. And this, so again, I'll go ahead and define it. So you look at K0 Z pi 1X. So again, the integral group ring. And just like in the case with the Whitehead group where there were some obvious elements, in K0 there's also an obvious element in there. So if you look, so this is equivalence class as finitely generated projective R modules. Well, R itself is a finitely generated projective R module. So you can throw away the obvious one. And so this is quotiented out by the class represented by Z pi 1X. And if you throw that out, what you get is this reduced K0. And this obstruction vanishes if and only if X is homotopy equivalent to some finite CW complex. So here are two concrete examples where you see, on the one hand, obstructions appearing in K1, in K0. There's also obstructions that appear in the lower K groups, but those are harder to describe, so I'll leave those. But hopefully this is enough motivation that you can see why topologists might care for these. All right, so the next question is, okay, so now how do we compute? So computing. So as you can tell from these examples, the main source of interest, at least for topologists, is the case of integral group rings. Okay, so K star ZG, so G a group. And so if you're trying to figure this out, what you probably do is you start with the simplest examples, and probably the simplest examples you could think of are maybe the case of finite groups, because there you can actually write things out. You know, your matrices are going to be of a given size are controlled. So let me first start with the case G finite and tell you what's known. So I'll summarize everything that's known here. Well, 1.5 boards. So Ki Zg vanishes for I less than or equal to -2. So it's an open problem whether this is true for every group. So conjecture. So it's true for finite groups, true for all G. So the vanishing of the K -2 and lower is unknown, but it certainly is true for finite. K -1, there's a complete answer. So yeah, so all of these, in the case of finite groups, these boil down to basically representation theory plus number theory. So all the results I'm putting in here use techniques from that. So yeah, so in this case, K -1 ends up being always some number of copies of Z and some number of copies of the cyclic group of order 2, where R and S are explicit. And so explicit here means in terms of the representation theory of the group G. So for example, well, yeah, the formulas get complicated, but yeah, you need to know the representation theory of G, both over the rational, over the p-adics, and over finite fields. They all enter into the formula. Question?
By Z, you mean Z mod 2?
Oh, Z sub 2, yeah, this is cyclic group of order 2. Sorry, cyclic of order 2. Yeah. Okay, so K -1 is pretty well understood. K0 is less clear. So K0 Zg. So this is always finitely generated. But there's no easy formula the way there is for K -1. And so here I should say both of these results are due to Carter in the early 80s. So this is finitely generated. There's computations in some cases can be carried out. So in particular, I think it's the K0 Zg has been identified for all groups of small enough order by computer programs. For certain classes of groups, so for example, if G is a cyclic group of order n, there one has some predictions as to what it should be. These predictions typically involve well-known problems in number theory. So here, you know, but given a concrete finite group, one can at least, given a concrete finite groups, a strong enough computer, an infinite amount of time, one can compute that. Okay. K1 Zg. This one has a more or less complete answer, so plus or minus G. So this was the part that we threw away to get the Whitehead group, plus two other pieces. So a piece that's called SK1 Zg. So this here is purely torsion. And there's techniques for analyzing this piece, plus a free part, and z to some t. And here t is explicit. So the rank of the Whitehead group is explicitly computable. There's some simple formula. You count the number of simple RG modules, and you subtract the number of simple QG modules, or something like that. And that gives you the rank of the Whitehead group. But the torsion part is less clear. And here there's some recipes for calculation. But again, these involve representation theoretic and number theoretic tools. Okay. Now, you'll notice I defined lower K theory, I didn't define higher K theory. The problem with higher K theory is if you think of how our definition for lower K theory was formulated, we use this suspension functor. So one way you could try and do higher K theory is you'd want to, you take a ring and then you find something that suspends to it and then define it to be. The problem is that the suspension functor is very much not surjective. Right? So most rings are not suspensions of other things. And this was actually a big problem. It took a long time for people to figure out the right definition for higher K theory. Eventually, this was done by Quillen. So higher K theory. So this was the work that Quillen got his Fields Medal for, was formulating the correct, and the higher K theory, yeah, it's defined as homotopy groups of a certain space associated to the ring. But yeah, so I won't discuss that at all, other than saying it exists, but it's much more complicated. So. Okay, right. So this is sort of the state of the case when G is finite. And so all of this is sort of scattered work by various people over many years. So then you might ask, okay, so after finite groups, what's the next simplest class of groups? So, cyclic groups. So Z, or maybe things that are a little bit more complicated, so virtually cyclic groups, right? So there I did finite, so G now virtually cyclic. And if you think of a virtually cyclic, so reminder, so i.e., so G contains a cyclic group as a finite index subgroup. That's what virtually cyclic means. So in particular, right, there's the finite ones, and then there's those that have a Z as a finite index subgroup. So there's an element of infinite order, and the quotient is finite. And so for virtually cyclic groups come in two flavors. So there's two types. So the first type is the following. So they come as, right, so a finite group, semi-direct with Z. So here, F finite. Or the other possibility is they come as an amalgamation where H has index 2 in the GI, and all these groups are finite. Okay. So those are the two possibilities. So in parallel to trying to figure out what the situation is for finite groups, people started looking at the next most complicated case. And here's where things become interesting. So for case 1, we have an old result of, well, Bass, Heller, Swan. So let me tell you here what happens. So here's the theorem. So if you look at the K-theory of the ring R T T inverse, so this is the ring of Laurent polynomials. This ends up being isomorphic to the K-theory of R. So maybe I should put it, so let's say Kn of R, direct sum Kn minus 1 of R, plus two additional terms. So I'll call this Nk n of R. Now, so why is this? How does this relate back to this example here? So think here R as being ZG, where G is a finite group, or maybe ZF, F finite. Then Z of F cross the integers. So this is an example of an infinite virtually cyclic group where the semi-direct product is actually a product. Then this thing here is exactly R T T inverse. Right. So the T T inverse factor here, you think of the Z's as being the exponents decorating here. Okay? And so what this is really doing is it's really dealing with the product case up here. Okay? And what you see is that when you take, so in this case, if you specialize to F cross Z, saying that the K-theory of the integral group ring of F cross Z looks like a copy of the K-theory of the integral group ring of F, plus a shift by 1 in dimension, plus some other mystery terms. So this I'll return to. So these are called nil groups. So K-theoretic nil groups, which, yeah, I'll say more about later. Now, so there's a version of this that corresponds also if you've got a semi-direct product, then there's a twist. In that case, this turns out being a non-commutative version of the Laurent polynomials, where as you slide the t past the r, you induce the twisted version. And there's a version of the Basque-Heller-Swan formula as well that allows dealing with semi-direct products. But maybe in the interest of time, I'll leave that out. But let me give you one other theorem. So this is Waldhausen, which deals with the second case. Okay? So the K-theory is a covariant functor. So given this sort of situation here, the group H sits inside G1, it sits inside G2, and each of the G1, G2 sit inside the entire group. Right? So so let me say gamma G2, we have a long exact sequence. Okay. And the long exact sequence takes the following form. So you've got Ki ZH, Ki ZG1, direct sum Ki ZG2, Ki Z gamma, Ki minus 1 ZH, dot, dot, dot. Okay. This is almost true. Just like back here, there were some mystery terms appearing. Here, there's also some mystery terms. You've got to quotient out by something which I'll call the Waldhausen nil. And strictly speaking, I should have called this the K-theoretic Bass nil group, since Hyman Bass was the one who introduced that. Okay, so this in principle allows you, if you understand the K-theory of finite groups, these allow you to go to virtually cyclics, well, provided you know something about these missing terms. Okay. Now here's a question. This should kind of look, if you're a topologist, this should look a little bit familiar. Right? If you look at this here, and you look at this formula, these are hinting at some sort of topological structure. Right. So does anyone? Yeah? Yeah. So this kind of looks like a Meyer-Vitouris. Exactly. And this, on the other hand, looks kind of like the Kunith formula. If you take a product with a circle and you take the homology, so this here is a Kunith formula. Right, so on the level of fundamental groups, crossing with Z is like taking a product with a circle. And the homology, when you take a space, you take a space, cross it with a circle, and you look at the homology of those two things. They're related by the homology of the whole thing is the base plus the base shifted by 1. Okay. So now this should strongly suggest that these functors that were defined in some crazy way really maybe are somehow homological in nature. Okay? So this suggests that algebraic K-theory is a, well, ... homology theory. And the ... here is that to make this precise, you need some adjectives. And the adjectives are equivariant, generalized homology theory. Okay, so it's not your usual homology theory, but there's other homology theories. If you look at the Eilenberg-MacLane axioms. Eilenberg-MacLane, do I have those right? Is it yeah. So the axioms for homology, there's a dimension axiom. So if you weaken that, you throw that out, you get what's called a generalized homology theory. And the equivariant just means that the homology theory is for spaces equipped with a group action. Okay. But you can kind of see where this comes out naturally from computations. You first compute for finite groups. Okay, there it's not at all clear what's going on. It looks completely representation theoretic and number theoretic. But then as soon as you move to the next simplest examples, you start seeing formulas appearing that are strongly suggestive of homology. Okay? All right. So now let me go ahead and, so now Farrell and Jones enter the picture. So this is, early 90s. And they made this precise. Okay. So here's a fact theorem. So this was in their original paper introducing the isomorphism conjecture. So there exists an equivariant generalized homology theory. So this is going to be denoted KZ with the following property. Okay, so for any group, G, to evaluate an equivariant generalized homology theory, I need to give you a space and the group acting on the space. So here it's the equivariant G homology of a space. And what's the space going to be? Well, if I don't know anything about the group, there's only one reasonable space for it to act on, namely the most trivial thing. So the group acting on a point. So on a point. So if I look at the equivariant cohomology of a point with coefficients, so this special generalized equivariant cohomology, this ends up giving you Kn of Cg. Okay. So there is a homology theory. So, you know, this functor was defined in some crazy algebraic way, but really what's hiding behind it, at least for when you restrict to group rings, what's hiding behind it is some generalized cohomology theory. Okay, now, so that's nice, but now I can tell you what the Farrell-Jones Isomorphism Conjecture is. So how long do I have? 7 minutes? Okay, till about 10:20. Okay, so great. So now let me go ahead and tell you what the Farrell-Jones Isomorphism Conjecture is. Right. So now, so one thing that came out of the simplest cases of finite groups and then virtually cyclic groups is that, you know, if you were to guess naively, you might say, okay, in the best possible world, if we know the K-theory of finite subgroups, then we know it for the big group. Okay. So if you look back here, this is what would happen if these nil groups didn't appear. Right? The K-theory of F cross Z would just be two copies or a shifted copy of the K-theory of the finite group. Okay. But that's not the case. There's some mystery term that appears when you pass from finite groups to these virtually cyclic groups. So now as you go to more complicated groups, it's not clear what happens, right? So let me now, yeah. So here's the Farrell-Jones isomorphism conjecture. So I'll give you the informal version first. So for any group G, so, or maybe I should say for the group G. Says that the K-theory of ZG is completely determined by the K-theory of its finite subgroup. So, sorry, of its virtually cyclic subgroups, where V ranges over all virtually cyclic subgroups. Okay, so the conjecture is saying there's no other mystery terms that appear. If you can understand the K-theory of all the virtually cyclic subgroups, and if you're given the group G, then all you need to do is you need to find all the virtually cyclic subgroups in G, and from their K-theory, that's going to build up your entire K-theory of the group G. So this is saying that all the complexity that appears in algebraic K-theory appears at the level of virtually cyclic subgroups. There's nothing else, nothing more complicated beyond that. Okay? So this is the informal statement. Right. So the formal statement is a little bit messier. So let's see. Do I want to say something about that? Yeah, so for the formal statement, one needs to define classifying spaces with isotropy in certain families of subgroups. So maybe I'll go ahead and I'll just put up the definition. I'll get to the point of writing at least the formal statement, and then we'll call it quits. So let me give you a definition. So F is a collection, so a family of subgroups if it is closed under conjugation and passing to subgroups. Okay, so let me give you some examples. So examples. So if you just look at the trivial subgroup, that's a family of subgroups. Okay, so this is just the trivial subgroup. If you look at the family fin of finite subgroups, so now I give you a group G, I look at the collection of all finite subgroups, that's a family. Okay, so it's closed under conjugation. If I take a finite subgroup and I conjugate it, it's still finite. If I take a subgroup of a finite subgroup, it's still finite. So this is another class of, you can look at VC, so this is virtually cyclic. Right? You've got something that's virtually cyclic. You conjugate, it's still virtually cyclic. You pass to a subgroup, it's still virtually cyclic. And you know, you can take your favorite. You could look at like virtually abelian groups or abelian subgroups, or you know, there's lots of such families. And maybe at the other extreme, there's all, which is the collection of all subgroups. Right? So those are all examples of families of subgroups. So now, associated to any family of subgroups, there is a classifying space that classifies group actions with isotropy within the family. Okay. So a space, so a G space, complex X is a model for E. So I've got a family F. I say I've got a model for EFG. If it has the following properties, so if I take any subgroup H that's not in the family, then the fixed set, so this is the H fixed set, is empty. And for all H in the family, the fixed set is contractible. Okay? So this is what it means to be a model for EFG. It turns out that this is unique up to G equivariant homotopy equivalence. So this gives a well-defined object up to G homotopy. And you know, it might be instructive to think of some of these examples. So for example, if you look at the trivial subgroup, then this is just a contractible space because of the second condition with a free action because of the first condition. Okay? So example is, so E trivial G is just the usual EG, contractible space with free G action. At the other extreme, if I take the family all, so what's a model for that? Well then, now if you look at this, then you're always in the second case. So you want a space on which G acts with the property that if you take any subgroup and you look at the fixed set, it should be contractible. So there's also a very natural model for that, just a point. You take a point, there's only one G action on it. You take any subgroup and you look at the fixed set by that subgroup, it's just that point. Point is contractible. Okay? And then these other things sort of interpolate in between. So for example, so the one for fin shows up. This is sometimes called the classifying space for proper actions. And yeah, so why are these called classifying spaces? So if you've got any GCW complex with isotropy within the family F, then there is an equivariant map from that space to your model space. Okay, so it's got this universal property that all G actions with isotropy in the family map to that model space. All right, so now, so how is this related to that right here? Right, so when you've got an equivariant generalized homology theory, anytime you've got an equivariant map between spaces, you get an induced homomorphism. So now I can state the formal version, so maybe I'll put it right down here. So the formal version is the following. If you look at the point, so this is the K-theory of ZG, what you might be interested in computing. On the other hand, any G space has an equivariant map to a point with the trivial G action. And so here, if I take any G space, there's a corresponding homomorphism. So the Farrell-Jones Isomorphism Conjecture says that if you understand what happens with virtually cyclic, that's the worst possible case. And so it's this. So if you take a model for EVCG, this is well defined up to G homotopy equivalence. The corresponding homology group is well defined. You get an induced map to the K-theory of the integral group ring. And the conjecture is that this is an isomorphism for all n. Okay, so this is the precise formulation of the Farrell-Jones isomorphism conjecture. Now, okay, so I'll stop here. Baum-Connes conjecture, exactly the same thing, but for a different functor. There it's the topological K-theory of the reduced C-star algebra of the group. That's the functor you're interested in understanding. You run the same scheme. You compute it for a few easy examples, finite groups. Then it turns out that as soon as you go to virtually cyclic, nothing new appears. So there, but there's similar formulas, similar to the Bass-Heller-Swan, similar to the Waldhausen formula for this other functor, this topological K-theory of the C-star algebra. So again, you guess, well, maybe there's some homology theory floating behind, and there is. And then the Baum-Connes conjecture is exactly the same statement for that other homology theory, but there you should be able to compute everything from the finite subgroups. So the only change is that, well, it's a different homology theory, and the space you apply it to is E-fin instead of EVC. So this is a general phenomena if you've got a functor on the category of rings that you're trying to evaluate on integral group rings. You try to see how homological does it look. If it looks pretty homological, you make a guess as to, you try to construct first the equivariant generalized homology theory, and then you can stick in a model space which concentrates, you know, the part where the homology, where the K-theory is doing unexpected things. So, and I shall stop here. Yes.
In the Farrell-Jones theorem, you say with coefficients in KZ,
Yeah.
every group reacts on that space?
So, yeah. So this is a generalized homology theory. So there's some spectrum associated to it. The way this is computed, when you compute equivariant cohomology, what you're really doing is you're looking at the ordinary homology of the Borel construction applied to this. So you're really looking at the homology of BG with this coefficients in this spectra. So you're really looking at, you know, the usual definition. You smash and you look at the stable homotopy groups of the resulting spectra. So.